Right. After exams, the exams are done, but work is not done. Okay, electromagnetic radiation. Earlier this year, we'd spoken about EMR, electromagnetic radiation, and we'd covered a bit of work on it. Can anyone remember what we covered on this section of work? This year, yes. On light. Redshift, when we're dealing with the Doppler effect. Okay? Remember we spoke about line emission spectra? Remember those spectrums or spectra where you just saw individual lines? And we said that those lines could shift. Remember that? That was the Doppler effect. That's dealing with light. And I showed you that diagram of long waves on one end and then very, very short waves on this end. Remember that? Frequency we dealt with, wavelength we dealt with, the energy of the waves, etc., etc. We're just going to quickly go through all of that again, and then we're going to deal with the photoelectric effect. Once we're finished with the photoelectric effect, so really what we're going to do today, in this, or not today, but in this chapter, one, we're going to go through light basics. And that will be this lesson today. Right? This afternoon, we will go through the photoelectric effect at our extra lesson this afternoon. And then the last section will be spectra. We've already dealt with 2/3 of that earlier this year when we touched on spectra in the Doppler effect. So that really is what it is. We should hopefully be finished tomorrow or maybe Wednesday. Okay, which leaves us Thursday for revision. Isn't that nice? Okay, first of all, can anyone tell me what exactly is light? That's another name for it, yes. There are lots of ways of describing light or telling me what it is, or some people say light is a wave, some people say light is a particle, yes. So there's a difference of opinion. Some people say it must be both. It consists of oscillating, which means changing, magnetic and electric fields, so one causes the other, yes. But getting down to really basic things like we would teach a grade 8. Light generally moves in a straight line, but it can be diffracted, it can be reflected, which means it gets bent, and it can be diffracted, refracted, and reflected. What else can light? What is light? Light is energy. That's critical. Light is energy. Okay, so that's step number 1. So, light basics. Okay, we're going back to that there. Step number 1 is light is a form of energy. I will give you notes, you don't have to write it down. We also said there are 2 ways to transmit energy. What are the 2 ways to transmit energy? No. Contact and non-contact, but when we're dealing with light, the whole concept of contact and non-contact becomes blurred. But you mentioned it earlier, one of you mentioned about the dual nature of light. Light could be a particle or light could be a wave. Now that touches on the 2 ways of transmitting energy. One, by wave, and 2 by particle. Those are the only two ways that we have of transmitting energy, by wave or by particle. Example, a wave, the photoelectric effect. Now this means nothing to you at this stage, but it's an example where at the end of this chapter you'll understand it, because we will have done the photoelectric effect by then. Right? Photoelectric effect, who of you have got a calculator that it works on a photocell? In other words, you don't have to put new batteries in it. Okay? Some calculators nowadays work on photoelectric effect. They've got a photocell. The light that falls on that calculator provides the electricity for that calculator. Okay? That's photoelectric effect. But the light is bombarding that photoelectric cell with particles. Do you agree a bullet transmits energy? I can stand on this side of the class and I want to sort out Esther. Bah! Shoot her. Okay? I've transmitted energy from the gun. All that energy stored up in that bullet, in that cartridge. Bang, when the bullet hits her, it sorts her out. Punishes her for failing that last test. Okay, so I've transmitted energy from the gun to Esther by means of a particle, a bullet. You agree? Okay? It's the same as if I took a baseball bat and I hit you over the head, Shara. Okay, because you were speaking in class. I've transmitted energy from my arm via the baseball bat. The baseball bat is like a particle, isn't it? But could I stand here and say, I'm going to punish you, and don't throw anything at you or shoot anything at you, could I? No, not possible. Unless I could shoot waves. That would be quite useful. Oh, sorry, I've got them all swapped. This is the wrong way around. My apologies. Just put a little arrow there. It's easy. Okay? So bullets. Anything else that transmits energy in a particle form? A fist. You agree? The fist becomes the particle. Okay? And by wave would be sound, yes. And I'm putting a question there with sound, because sound is a wave, but it uses particles, vibrating air particles. Okay, so therefore question mark. But how does the sun get its energy to us? Or the sun's heat. Let's just put the sun's heat. How do we feel? How does that heat get to us? Okay. How does that energy get transferred way out there to us? Via waves. The sun's heat. It could also be spoken about as particles. Or a boat on a pond. If those particles had mass. Why must all particles have mass? Do you accept that you get some heavy particles and you get to get some light particles? Yeah. And you think it could get even lighter? You could have a polystyrene particle which is pretty light. And if you go even lighter, maybe it's got no mass. Why not? Prove it. Why? Not everything has got mass. Has light got mass? What's the weight of the sun's rays that are falling on you today? So now, you don't define a particle by the fact that it's something that has mass. No, electrons do have mass. But anyway, we're not going to go into that now, otherwise we're not going to finish the section of work. But my apologies. Waves, things that transmit energy by waves, sound, the heat from the sun, okay? Boat on a pond. If you've got a boat floating on a pond, little toy boat, and you want to knock it over, you can either throw stones at it, that's by means of particles, or you can make waves on the side of the pond, and that can maybe tilt the boat over. That is water, because it's very difficult to be able to show waves here on the Earth without using a medium through which those waves can travel so that we can see it. Otherwise we can't. Okay, so apologies for using examples that do also use a medium. Let's hand out page 1 of your notes. That's 2, 3, 4. I think I may have given you one extra page over here. One for you and Esther. There should be a spare one for Daniel. Thank you. Right, let's just run through that page. As I say, there's nothing new on that page or anything. We've covered this when we dealt with the Doppler effect, so I'm going to go through it quite quickly. Let's just quickly read through it. General information about light. Light is energy. There are two ways of transferring energy, either by a particle, like a rock or a bullet, or by wave, such as a surfer. Okay? I do agree that that example, you could say the water is a particle, but it's a difficult one. But if you think about it with a wave, does the water actually move? Which way does the water move when a wave is flowing from the cupboard to the windows? Which way is the water moving? The water is only going up and down. Okay, which way is the surfer moving? In the direction of the wave. So the energy is actually moving towards the beach. You agree? From the ocean to the beach. But the water itself is only going up and down. If you had a little empty container like this floating in the water, that empty container wouldn't rush into the beach. It would simply go up, and as the wave passed underneath it would go down. It would still be floating there. But your surfer would pick up the energy because of the way that you catch that wave. That surfer would pick up the energy of the wave, and the wave's energy would push it into the beach. Okay, it would gain that energy. So that's to show that you can transmit energy without a particle actually moving in that direction as well. The wave, the water particles move up and down, but the actual surfer moves forward because of the energy of the wave which is moving forward. Then, light. Next question there, third line. Is it a wave or is it a particle? On the left of the page, I've got a few things that prove, and notice I've written prove in inverted commas. Can you see that it's inverted commas? Those photocopies are not too clear, I'm afraid. But what proves that light is a wave? If we're saying that light is a wave, then we need some proof. If we're saying that light is a particle, we need some proof. And the proof of the fact that light is a wave is the fact that light undergoes diffraction. Can anyone tell me what diffraction is? Anyone have any idea of what diffraction is? Not? Yes. Diffraction, you may want to just supplement your notes. If you had a solid barrier blocking waves that were coming into a harbor. So here's your ocean. Okay. Here are your waves approaching. There your waves approaching, and here you've got a harbor wall. What would one normally expect these waves to do? You'd only get a little portion of wave going through. Do you agree? And that's what you'd expect. You agree? Only that little bit would go through. Right. But in actual fact, what happens is the wave curves like that. And you get a wave going through that more than just that little section. That type of thing happens. All right, so your wave starts bending outwards. Right. The bending of light when it passes through a narrow gap, like I've shown there, or past a sharp edge. All got that? Okay. What's the other thing that proves that light is a wave? We said one of the things, let's have a look. If this was a bullet coming through here, imagine that there was a boat, a military warship, firing bullets, a machine gun firing bullets through this gap in the harbor wall. Would those bullets spray out and diffract and bend like that? No, they'd carry on the straight line. Unless they hit the harbor wall, then they would ricochet. But if they never hit anything, they'd just carry on in the straight line. So particles don't bend when they go through narrow gaps or past a sharp edge. They carry on in the straight line. Waves do bend, okay? And as we can see, water waves, they bend. Light waves do the same thing. We'll look at that just now. The other thing is called interference, and you may have dealt with this in grade 8. Interference. I'd like you to turn in your books to page 401. Okay, now that first sketch on page, in fact it's a photograph, 401, that shows you light passing through a narrow slit. Now much narrower than a harbour wall, than the gap in a harbour wall. Probably 1/100th of a millimeter thick. Okay, shining light through it. Look what's happened to that light. It's spread outwards. Do you agree? Okay. Figure 11.13. Also on page 401. Shows that picture in a little bit more detail. It's more finer. Now imagine here you've got not waves of water approaching a harbour wall, but let's say you've got green waves of light. So you're shining green light to this narrow slit. Now we all accept that the light that comes through there is not just going to be a narrow slit of light. You agree? What's that light going to do? It's going to bend outwards. So if you were over here looking at this, you wouldn't just see a narrow slit of green light, you'd see a wave of green light that's bending outwards. Agreed? What happens, I'm not going to go into it, is that these waves start overlapping with each other. They start overlapping with neighboring waves. Okay? And you know from your early information on waves that if you have two waves like that, that's one wave, and let's say we've got another wave that looks like that, and they overlap. What happens when those two waves overlap like that? The green wave and the red wave. The green wave and the blue wave. You're going to get constructive interference and destructive interference. And your resultant wave, your net wave of the two, when you add them together, is going to be a wave that's that much taken off there. You agree? So your resultant wave is going to look like that. What would happen if I had two waves that were identical? Okay, now you agree this green wave and that green wave are identical. They're the same light. And I put another wave, but exactly half a phase behind it. What are you going to get? What's your resultant wave going to be? You're going to get nothing. Flat. No resultant. Now, when you get waves overlapping, this row of waves overlap with the next door wavelets and with the overlapping with waves in front of them and behind them, you start getting points where you get a crest overlapping with a trough. And what are you going to get at that point? Nothing. You're also going to get points where you get a two crests, two troughs, etc. What are you going to get there? Not the same. You're going to get something which is double the height. Okay. And that second picture on page 401, where you got light, then a black patch. Light, black patch. That's a result of what we call interference, where the light goes through a gap and it's not just carrying on in a straight line, it's bending. And because of the bending, the waves start mixing together with each other. Waves from one row start mixing with waves from the other row. We won't go into the exact detail of it now. Okay? And that leads to spots where you get zero interference, in other words, the black line, that's no light, and spots where you get double because of constructive interference, and that corresponds to the bright green bands. Understand that? If you don't fully understand it, don't panic about it. Let's just have a quick look if I did the following. And this will help you understand this interference pattern a little bit better. Okay? What I'm going to give you now is what is called double slit interference. And it's a little bit easier to understand than just with a single slit. So let's say I had a barrier in the boundary, a gap in the barrier, like that. Can anyone tell me what will happen with the waves here? They'll go through, do you agree? All happy with that? What will happen here? They'll go through. Oops, that's not so good. There. Happy? Can anyone tell me what's going to happen where I put these red dots? First of all, what do these lines represent? What part of the wave? They represent the crests of the wave. Okay, so they represent, so you can imagine there's a crest, there's a trough. Crest, trough. Crest, you understand what I'm talking about? So what does that empty space in the middle between two green lines represent? A trough. Trough. Crest, crest. So what does that line represent? And this space in between? Now, what have I got overlapping at that red point? Two crests. So when two crests overlap, what does that give me? A big crest. And that point there? Two crests. Big. What have I got there? A deep trough. You agree? Because it's a trough from this wave, yeah, and a trough from that wave there overlapping. All agree? So these points where I'm putting dots now represent either deep troughs or high crests. The high crests are nice and easy. The troughs, there we go, etc. There we go. Right. Right. What do you notice about those lines that I've drawn? Or those dots that I've drawn? They form a line. They form a line. So all the spots where you either got high crests or deep troughs tend to end up as lines. Let's have a look at the spots where I'm going to mark with a blue dot. The crest of one with the trough of another. You agree that's a trough running around there? And that's a crest there. Crest and a trough, crest and a trough, crest and a trough, crest and a trough, crest and a trough. What do you notice happening? Now what happens when a crest overlaps with a trough? No, you get nothing. And what happens when you've got no light? What color does that look like? Black. So these lines here are black. Okay, and same over here. And the red dotted lines are bright patches. What does that correspond to in that sketch? You see why? So if I had to put a screen here, what would I get? Black, green, black, green, black, green. That's what we call an interference pattern. Now that's when I use how many slits? 2 slits. Easier to understand with 2 slits. A similar thing also happens when you've only got 1 slit. Quite complicated to work the maths out. It's got to do with waves being about a half a wavelength behind each other when you turn them at an angle to each other. Okay? It can happen with a single slit or a double slit. But the important thing is that you get a pattern which is called an interference pattern, okay, from light waves overlapping. Now that would never happen if those were bullets traveling through there. The bullets would just bounce off each other. Would you get beautiful patterns like that for me? No. So the fact that you get interference happening, the fact that you get diffraction, the bending, that proves that light is a wave. Okay, that does prove that light's in. Yes, it does. So what happens if you've got a math theorem that can prove one thing and can also prove? then you've got a problem. You agree? And that's what we've got in science. We've got a problem. No one knows what light is. Okay, thank you. We'll stop the lesson there. I'll see you this afternoon.